Okay, lecture 20. I guess that today's lecture will be quite short because we have already done many things required for lecture 20, but just wanted to apply it to our FinFET example, so smaller version of a FinFET example, and to estimate the performance of a FinFET. Okay, let's come back to our FinFET. As you can see here, this figure or this structure is the one simulated by our ASAP PDK authors. So they made their own TCAD simulation for this structure. So as you can see, diamond source drain and spacer, metal gate, yes, source drain contact, everything is quite common and we know it, and we wanted to build a similar thing, so not exactly same because everything is not open to us, especially some length scales are not that certain, but anyway we can at least try to mimic its performance. So I want to make a simplified version of our inverter example. Our inverter example considers 3 fins for N MOSFET and 3 fins for P MOSFET, so it just consider the complete inverter circuit. However, in this time, I just wanted to make a single fin N MOSFET. So in terms of its area, more than 1/6 times smaller than its original version. And now let's just start. So in this case, we need to, due to so due to the limitation of a machine program, so we need to set our size multiple of 4 or 8 or power of number 2. So in this time, yes, that is my suggestion. So this is 2 times of CPP. CPP is 54 nanometer in this technology, and so I just set 2 times of CPP. Why I did that job? Because I wanted to consider the shape of source and drain as exact as possible. So if we cut somewhere except for that spacer region, then its source drain epitaxial growth is distorted, so I was not able to get a similar behavior. So that's the reason why I just wanted to do it here. So this 27 should be regarded as the 10 for our half dummy gate, and also 9 for our spacer, and also 8 for our half source and drain. So now we will consider this just a full length of source drain region, but well, so maybe we can later try to make a short, smaller version, but right now I will just show you the full scale transistor only once. And another one is y-directional coordinate. In this case, usually we assume fin pitch of 27 nanometer. It means that if we have one fin and the next fin, so we have a pitch of 27 nanometer. However, in this case, I just wanted to make a isolated fin. So if we have a fin, then if we so 27, and if we go to only 10 nanometer, we will find the area of our area governed by this next fin. And if we go to another 10 nanometer toward the positive y direction, then we will see so another area governed by another fin. So actually the area for single fin is just 10 nanometer and 10 nanometer for each direction, but in this case I just allow quite a wide area, so because I want I don't want to make such kind of merged or some distortion in its diamond shape. But please note that in our Ångström-Craft code, we are just using cubic voxel. So therefore, we cannot exactly reproduce the shape of our diamond structure shown here, the diamond source drain structure. So we wanted to just mimic as close as possible, but from our starting point, it's not inherently possible. So please allow this kind of error, shaping error. So I just wanted to isolate the fin, and yes, prepare a fin. So next part is quite common, so I just wanted to quickly move on to next part and next part. So now you have fin and STI, so just label them. This is STI, and this is bulk silicon. So how thick is it? It really depends on your choice. So I think that actually we don't have to have a thick bulk silicon case, because that is not contributing to the electrical property, but it takes a lot of mesh point in our implementation. So if you wanted to make efficiency, then just to make this bulk silicon part very short. Okay. And in this example, following our previous work, just took this fin height of 32 and STI. This is its thickness is 30 nanometers. So ratio is almost close to 1:1. So also this is STI part is not that well important, and in reality, so we should consider that in many cases compared with this active fin, so we have sometimes the even taller part of this STI covered part in our fin shape. So therefore this 1:1 matching is not that mandatory. So just to concentrate on this fin part, and after that dummy gate. So as I told you before, in order to make the as accurate as possible description for this source and drain region, so I just introduce this half dummy gate and half dummy gate. These are not actually used in our device performance, because this is just dummy gates, and after that, that is covered by also later, that is covered by gate terminal. However, in many cases, that gate terminal is just left as unconnected to the voltage sources. So that just left floating. So usually that doesn't make any kind of contribution to the conduction. But in this case, anyway, I just included it because I wanted to make some correct description for spacer. The only reason why I introduced this dummy gate is this dummy gate allows us to introduce spacer, and once we have a spacer, then we can generate the source and drain shape correctly. So that was the main reason. So if you can make spacer by some other means, for example, since we are just using our Ångström-Craft code and we can make any kind of geometrical operation, so if you can make this spacer directly, then you can skip this dummy gate formation part. But just to follow fabrication process at least roughly, so I introduced this kind of a dummy gate, half dummy gate. This is just 10 nanometer long, so we must consider that there is a mirror image of that dummy gate in this part and also in this part. And also here we have one thing. So actually, on top of this dummy gate, always we have also hard mask. So without actually hard mask, all kinds of this process becomes quite complicated, because hard mask is from, as you can see from its naming, hard mask is much harder than the others, so it can predict our structure from etching process. But in this case, we just consider dummy gate. So please think that this dummy gate is not solely dummy gate, but combination of the original dummy gate and hard mask on top of it. So I just wanted to make it simple. So then spacer, spacer. Oh yes, spacer wasn't 9 nanometer thick, so this one becomes a spacer. And after that, we make a very shallow fin recess, only 5 nanometers. So this level is a fin top level, but this one is just 5 nanometer thick. So during preparing this presentation material, always this part is one of the difficult part to me, because in many cases it seems like that people have tested many different recess depths for this fin recess. For some, they make it very shallow recess, but also when we have a TM image taken from other companies, then sometimes we can see that the entire fin part is fully recessed, and even underneath of this STI part, we can see some part of this fin is so subfin is etched away. So it is not very clear how deep this shell fin recess goes, but in this time I just took very shallow one, only on slightly etched away. After that, we can try to make a source drain epitaxial growth, and for this fin is really isolated, we can allow them to grow quite sufficiently. So that is the shape of my selected source drain epitaxial growth. Of course, if you stop a little bit earlier, then the shape is a little bit smaller. And if you allow a little more, then what will happen? Then it will grow. But my suggestion is, please do not make this source drain epitaxial growth hit the wall, hit the boundary of our y-axis. So this is y-axis, and here we have boundary of our emulation domain. So if it hits the domain, after that it cannot grow any further, because there is nothing in this world. So now shape becomes a little bit distorted. So if you really wanted to expand it wider and wider, then please allow even wider domain, emulation domain, for your scheme. So instead of, for example, 48, so instead of starting from this 48, if you increase it by amount of 4, 8, 12 something, then you have a sufficient margin to allow further growth. So please avoid this boundary hitting cases. And as I told you repeatedly, so in this program you can have this 45 degree between STI plane and this face. This becomes just a 45 degree due to cubic boxes, and that is inaccurate. In reality, the angle is slightly steeper, so we have more than 50 degree, but well, this is the limitation of our current implementation. Of course, in this case, dummy gates and spacers are not shown intentionally, and also we have to grow salicide on top of this silicon, so we need to add something, actually introduce some metal and apply heat, then it becomes the metal silicide. So it is used as a buffer layer between metal and silicon, but that part is also skipped in this simplified version. After that, dummy gate is removed, and this is corresponding to ILD 0. So interlayer dielectric 0 means that it's index. That is the very first one. And actually this ILD 0, who decide this ILD 0 height? That is determined by hard mask. Hard mask top is used as the CMP stop layer for this ILD 0 deposition. So simply speaking, we just put a lot of ILD 0 material. After that, do the CMP. But when it hits the top of our hard mask, then it stops. But in our case, we just treat dummy gate as a combination of dummy gate and hard mask. So we just stop at the top of our dummy gate. So that's the reason why the relation between our, how can I say, if we really look at the real TEM images, then sometimes you can see that here we have a spacer, and later we will have a gate. However, some cases you can find that actually gate is only formed up to this point, not overcoming our spacer, but I now just to go to this direction. So if you really wanted to be very rigorous about this MOL shape, then please try to consider also hard mask and its relevant thicknesses. Well, anyway, now dummy gates are eliminated, and now we can introduce oxide, but this is something we must mention in this case. In this example, I just introduce 1 nanometer thick layer deposition everywhere. So that is done with isotropic deposition. However, in reality, we first do oxidation of silicon. It means that only silicon now becomes silicon dioxide. So silicon nitride cannot make any kind of silicon dioxide. Also, other part cannot be oxidated. So sorry about that. But anyway, we cannot make oxide on top of other different material. Only for silicon we can make a very thin oxide. Although I say this is 1 nanometer thick, but its real thickness is not 1 nanometer. It is just 0.5 nanometer or 0.7 nanometer. Maybe this is the typical length thickness we have. And after that, we introduce high K. So if we are really rigorous about this situation, then let me just draw more schematically. Here we have a spacer, and here we have a spacer, and here we have a fin. So of course this fin should be considered as a three-dimensional structure. We are just see the projection. So if we can allow three-dimensional drawing in this time, then maybe this is the shape of our fin. Well, in this case, when we try to make oxidation, then oxide generate oxide formed only this side, top, and another side surface of a fin. Source and drain, this spacer is not oxided. But here, when we later introduce high K, then this is really deposition. So simply speaking, we can have high K, high K, high K everywhere. Also nearby this spacer, we can have also high K and also high K. So let me just draw it more ordered way. So let me just do it. Spacer, and fin. Then we have oxide. This one is SiO2, and here we have this part becomes high K material. Well, so that is the case we have. But you know, high K material, they do not contribute a lot of effective thickness to our transistor, because although we have EOT around 1.0 nanometer, slightly shorter or slightly longer, but most of them, or considerable amount of them, is consumed by this intrinsic silicon dioxide. After that, we have high K. Its thickness is typically 2 nanometer or 3 nanometer. However, due to its higher dielectric constant, its contribution to the electrical thickness is not that high. So, in reality, here we have just 1 nanometer thick silicon dioxide in our calculation, our emulation. But in reality, we have to have slightly thicker high K layer. However, its contribution to its capacitance is even lower than this 1 nanometer thick silicon dioxide assumed in our example structure. So that can introduce some differences in our electrical characteristics. So please understand this limitation. And after that, as I told you before, this part is tungsten. However, actually, in order to match work function, also we have to introduce a work function metal, and only after that we have a very narrow region that is filled with tungsten. But all kinds of that difficulties are just removed, and we added tungsten fill, and only work function of a gate metal is controlled in our G device step. So in this sense, this work function can be used as a fitting parameter for your IB characteristics to the experimental result. Okay, and also another one is final height from the STI top is said to be 60 nanometer in this case, because previous during our previous example, the final structure shows quite tall structure, so I made a little bit shorter one, but I'm not quite sure what is the exact height suitable for this a virtual PDK because there is no exact TEM image to be reproduced. So because this is not existing in real world, so I just make it in this time, this number. So of course you can change it. Okay, so I think that I have covered many of them. Got gate dietary also covering here, and actually this becomes a high K, but in its physical thickness it should be thicker, and in its electrical thickness it should be shorter. So, so well, that is the limitation of our current structure, but I think that it's okay. And this part is related with beyond fail. So front end of line is usually regarded as ended at this stage, and now we have to introduce this source drain contact. Maybe you can ask me this question. We have already made a source drain by selective epitaxial growth, and also we did the salicide. Yes, you did it, but the current situation is now you have a diamond structure, and this is in this case silicon for N MOSFET or silicon germanium in P MOSFET. On top of it, we have salicide. Yes, however, none of them are real metal. That is, they are regarded as a part of an intrinsic device. This is a transistor. And what we wanted to do is now make the connection between this transistor and interconnect. Then this part, substrate here, substrate contact means that now we have to add a certain amount of real metal to connect the higher level of integration and our intrinsic device. Then how can we do that? That is done in this way. So you know that this was the level of ILD 0. So you know that height was set by the top of our hard mask, and that was done. After that is at the end of our fail. Previously there was ILD 0. After that we introduce another layer called as ILD 1. This is once again silicon dioxide, and we make this very flat surface. And after that we do once again patterning, means that we do the lithography, but this lithography is not that tight in this sense. So please have a look at this structure intentionally made imperfect. So can you see it clearly? So when you have a look at the generated structure, you can easily find that the hole inside the ILD1 and the hole in ILD0 are different. So, so why? Because this one is spacer and this one is a spacer, and ILD0 is more or less a variant of silicon oxide, and also ILD1 is a variant of silicon dioxide. So simply speaking, if we allow selective etching, if the selectivity between spacer and oxide is high enough, then even though our opening is not that perfectly aligned to this underlying structure, say that in this example I just allow 5 nanometer mismatch to left side and right side. So simply speaking, this wanted window for our source drain is just 16 nanometer wide. However, I intentionally assume that, due to some certain reason, our margin was so large, so we made mistake to generate 26 nanometer wide pattern. Then what happens? Then that can even destroy all kinds of our fabricated device? No, quite luckily, due to the high enough selectivity between silicon dioxide and spacer, although in this part we have a mismatched line, but once after into this intrinsic transistor level, then that can be aligned. Only silicon part or only source and drain part is selectively etched away. So now we can successfully access only to this source and drain diamond region. Okay, so in this sense, it's not fully self-aligned. We need to make a certain patterning. When we say self-aligned, in its original sense, we do not perform any kind of photolithography. Everything is just based on pre-existing patterns. However, in this time, we are doing patterning, but this patterning is much easier than the other critical one. And using this margin, we can enjoy a lot of advantages to make this pattern very accurately. Okay, so although we have a little difference, but that is allowed. Anyway, we can certainly access to this source drain diamond region. So in reality, if we can have the ultimate capability to control everything, then maybe that can be better way, make it the perfect matched alignment. I'm not quite sure, because by allowing a little bit wider space, that allows us reduced the resistance in this part. Although that is metal, still metal can contribute a certain amount of resistance. So if that is wider, then we can have a lower resistance. So maybe there should be the trade-off. If you start from very narrow one, then, and if you can do it quite perfectly, then you can have quite much allowed it. I mean that, let's say that this is spacer and ILD 0 and ILD 1. Let's say that we believe ourselves, our capability, and just to open perfectly, just to match and try to etch it. Then what will happen? After that, we have a tight margin. So we can just place this source drain region shorter and shorter, because we can control it. However, if we just try, for example, 16 nanometer, and let's assume that we make a little bit mistakes, for example, 8 nanometer shift in our patterning. So let's say that this is the actual window we have made. Then what will happen? Then the actual shade for our metal, content metal, will be like this. This is not that good, because of course here we have a certain bottleneck, so that can introduce a quite high resistance. So instead of this exactly 16 nanometer, if we have allowed it, for example, 20 nanometer, in our patterning. Then even though we have made 8 nanometer shift toward, for example, one side in this diagram, left side, but still we have a larger portion of our ALD1 layer is covered by this metal. So we always think about process variation. We are not perfect, we are not omnipotent, so we should be able to allow ourselves a certain margin. Please remember that in order to make this structure we have done in the fab, the engineers spend a lot of their time, resources, money. Everything is already done it here. However, if we take too tight margin for this not fail but MOL or BOL, then what will happen? Our entire 1 month, 2 months effort, that is gone. So we never allow that kind of a failure in this later part. So if you make mistakes in the initial stage, then we can anyway rework, and it doesn't introduce much damage to our financial health, but it can make the serious result for our company, for example. So therefore, we have to allow certain margin. Fortunately, using the selectivity, we can have the process quite close to the self-alignment. This is not exactly self-alignment, but we do it in that way. That is also very important to so I think that I have no time to talk about this more recent. Okay, so I think that I have time. Okay, let me just think about this one. Now we have made it, then we must make source and drain contact and also gate contact. These are connected to the upper part of our wafer. So later here we will introduce interconnect, and we must make the connection between our interconnect and this intrinsic device. This is the level of our device, and here we have level of metal lines. So we must make the connection between them. Then where do we make this connection? Let me talk about this topic from now on. So fortunately we can have this one. Let me just draw. Here we have a fin. Let's say that this is gate, and of course here we have a spacer, and also here we have a spacer, and there is a spacer. Where do we have a source and drain? And here we have a source and drain underneath, and also here we have a source and drain underneath. Of course, this is not one single fin. Of course, there will be another fin running here and another fin running there. So please regard them as granted. Then we must make the connection from this external world metal lines into this source drain level. Then usually what we do is select one point. For example, oh, I like this guy. This is, if we pick this point, then if we dig out our ILD1 and ILD0, then eventually we will meet the one having diamond shape. Okay, so there is hidden diamond shape in this part. Okay, this diamond is covered by ILD 0 and 1. Then what we do is make just a patterning on this part and etching that part. So we can make access to this source and drain. Then now let me ask this question once again. Okay, that is the one we have seen up to now. Then what is the next thing? What is the thing we can do for gate? How can you access your gate line here, vertical line? So quite naturally, when you first hear about this technique, then you can say that, okay, there runs metal lines. However, that is running just the level of, yes, this line. So maybe you wanted to make it somewhere here or somewhere there, but that was not that easy. Previously, what engineers did was make a long metal line. Okay, then here we can make quite a safe alignment for our etching. I mean that now previously we introduced a certain etching in this part, dig out ILD0 and ILD1 and 0, then we will see this metal line, and this metal line is connected from the top. That was the case. But you can easily understand that is quite much of a waste. This part, who pay? So we must pay to make this kind of a connection. So previously, where do we use this kind of connection? For example, since we have a source and N MOSFET and P MOSFET, so pull down circuit and pull up circuit, and between them we have made a certain unused part. So maybe you remember. So let me just show you our where can you find our layout, for example. Okay. Although it's not exactly layout, but anyway, you can see that this part is aligned to our N MOSFET part, and this part is aligned to our P MOSFET part, and dummy gate runs vertically for this fins, and here we have some part. So usually we can place something in this unused space to make a connection to the external world. So let me just come back. But now people think that even this kind of action or space uses seems to be too much, because we wanted to scale down our standard cell as much as possible. But if we just keep this kind of thing, then we must spend a lot of space to make a connection, not for transistor. So instead of that, now we wanted to make the direct etching of our active layer, and we wanted to make this direct connection. Well, we can do it, but what's the problem? Why we did it in this line far away from this fin? What is the difference between this part and that part? Previously, in this case, there is no fin, so we are quite safe to do anything. But in this case, please think about this one. I wanted to make a connection to this metal line, so I made a hole. Then what will happen to this guy? means that now please do not think about this one. Yes, this is fully filled with ILD0, and here we have ILD1. Now the hole is not for source and drain, but we must make a hole or window for this metal line. I made it. Then make a hole here. Then we can access it to our tungsten field here. Good. But what's the problem? The problem is if we make any kind of mistakes in its alignment, then the separation between our source drain part and gate is just, in this specific case, just 9 nanometer. And if we make a little bit mismatched one, then we can see that this extended gate material, gate contact is quite close to our source drain part. Later it is filled with source drain. So if we allow this mismatch, then that is shaking here. Then even shortage between source and drain and gate can happen in this case. Of course, if we do not have fins there, as I shown you here, in this case, then we are quite lucky. We can do anything, because if we do this job, there is nothing. So please understand that situation. So what we have done is, although we have considered this just two layer, ILD0 and ILD1, intentionally, after fill this ILD0 with tungsten fill, then people intentionally once again etch away this top part. This top part is etched, and intentionally we introduce silicon nitride. Then they are just protected from this one. Also, quite similarly, our source and drain part, we introduce this so-called capping layer. And only when we wanted to use it explicitly, we make etching and explicitly remove this silicon nitride and take the good access to this one. Usually these silicon nitride capping layers working as the protection layer for our gate, source and drain region. So details are quite complicated, of course. However, please note that that is directly related to our effort to reduce cell area. Please understand, this is nothing related with the intrinsic device. Intrinsic device already done in our fail stage. But by changing where we make this kind of metal interconnection, not exactly metal interconnect, but MOL layer, we can significantly reduce the area of our standard cell. Although transistors are the same, but by changing layout or way of interconnecting them, that can introduce a significant reduction of area, and also, that is related with increase of integration density. If we can integrate more and more chips, then it provides us a sufficient amount of capability to change something. So we can make a bargain between our performance and area, or many different figure of merits. So we can do much better job. So actually, this is to some researchers or engineers, this one is regarded of the central concept of DTCO. Means that from my point of view, I'm a device engineer, more closely related to the field. So my first concern, my first interest is related with device architecture itself, FinFET, gate-all-around transistor, new concept of a transistor. But in reality, as an engineer in industry, you cannot suggest for next generation, instead of this FinFET, let's go to the gate-all-around transistor. Usually that kind of a serious decision is not for single person. So industry level movement is required for that kind of a huge decision. So in many cases, the freedom, our capability is how can we optimize this given architecture. So in that case, this kind of relatively small ideas, changing something, especially in terms of interconnect MOL layer, that can introduce a lot of advantages, because previously people concentrated on fail, because that was the key part where performance was determined. But now fail part is already much advanced, and we spend a lot of effort already to this fail part, and people think that maybe this MOL, the middle end of a line, that is the place we can get some advantages further. So that's the main contents of DTCO. But what I wanted to say is that was a little bit, once again, old time story. So people really enjoyed this kind of action quite a lot. So every year they publish it, very clever idea to squeeze their standard cell by changing some process to allow more dense integration, especially in terms of MOL part. But now we have already spent more than 10 years in this topic, so our current layout seems to be quite much optimized, and we are quite close to the end of this approach. Then what's the next? Then the next one is we have to consider our scope, our expand our scope even a little bit further. Consider slightly larger system, considering standard cell themselves, and try to optimize their entire structure by repeating this kind of optimization process. So that is regarded as the future of DTCO. But please note that although we call it as which name, DTCO something, it's okay. Naming is not that important, but point is we have to improve the performance, because improving performance is the key to survive in this industry. Okay, so I think that I just made a simple description about MOL part. So MOL also contains a lot of more issues, but let's just stop here today. And after that, we can just let's switch gears. And then now I will just explain meanings of our Armstrong-Craft code. This is more related with the actual exercise. Already in our previous lecture, we made a volume mesh successfully, but the success was done by distributing you the file and learn that file. So you did it, you made it, okay. But now let me just explain what is the meaning of each line. So this is taken from my own exercise. So depending on your naming convention, so regions may have different names. For example, deep instead of deep substrate, you can have substrate. Silicon instead of silicon bulk, you can say subfin. whatever. So I do not care about the naming. Please just have a look at in its structure. In this Ångström-Crafty input file, you can have the x directional and y directional and z directional sizes. So if you wanted to make it, then there should be the relation. Here we have n resolution, and this n resolution minus 1, that is used to power of 2. So that becomes 4. So please make this Lx, Ly, and Lz multiples of these numbers. So then you can ask me this question: can we use different numbers for n resolution? Of course. For example, if you can try to have a number 4, then your Lx, Ly, Lz should be multiples of number 8. Yes, so you can do it. So that is one thing. And here you have regions. Then here you have a material and name, and this name is corresponding to existing region names in your CGNS file. For example, for ILD0, I introduced the name ILD0. For ILD1, I made ILD1. So you can just name of your preference. And here you have a material. It's not your preference. Its name is given. For silicon, use silicon. Silicon dioxide, SiO2. So if you say the silicon dioxide in typed in a English name, then that doesn't work. So you have to say SiO2. Of course, it has some other nicknames allowed it to you, maybe, but please do not make any adventures on this one. Strictly follow the material names. In this case, we have 3 different materials: silicon, silicon dioxide, and nitride. Okay, although we have many different regions, so we have used 3 different materials. And in this case, I made a simple example without calling any further specification for doping, contact. I just land my example only with this one, and of course you have to have a parenthesis here. And when you learn it, then what you have is there is no doping at all, because we have not assigned doping, and no contact at all, because we have not assigned the context. But even without those capabilities, this one becomes the structure you have in this case. Now, this is corresponding to ILD1, one layer, and yes, here we have our intrinsic device, and this is STI level, and this is bulk silicon, and here we have a later body contact, but there is no body contact right now. And you can see some triangles corresponding to the surface of tetrahedra. So yes, it is already discretized with some meshes. For example, as you can see here, we have a relatively large elements, and for example, for this part, this is a source and drain, we have a much dense mesh generation. Because why do we have this kind of thing? Because we have assigned different resolution levels. So 0 level is for exactly the smallest one. So in this case, 1 nanometer spacing is enforced. However, for example, 1 means that we allow 2 nanometer spacing for, we can at least try to introduce 2 nanometer spacing. So resolution 2 means that we can allow trial of 4 nanometer spacing. You understand the reason why we have a power of 2. But point is, this is just a trial. You can try, but the shape of your structure is quite complicated and thin. Then although you try to introduce a 4 nanometer structure, but let's assume that your structure is just 1 nanometer thin, then what will happen? Try, fail, so 1 nanometer spacing is kept. That happens actually in our gate dielectric layer. This one, this highlighted one is gate dielectric layer, and that is really 1 nanometer thick and everywhere. So we cannot use this kind of messy coarsening approach for this one, and it takes about 30,000 vertex points only for this very thin layer. Well, I think that this is not the most efficient way, but right now we can just use this capability. And here we have around 160,000 vertex points, so that can introduce a severe burden for your workstation. So for example, right now the workstation I am using is fully occupied by my graduate students. They are learning some jobs, and also I try to learn my jobs, but my job failed because there is no enough resource for me. They already occupied resources, so therefore that's the reason why, although I'm showing a relatively large structure containing surrounding source and drain, but I think that for your own purpose later, it is better to make an even miniaturized structure, including only half of your source drain and half of your source drain. Maybe you can eliminate this part from your constellation. Also, this part you can also cut this unwanted silicon subfin or bulk cases. So please concentrate on only the very intrinsic part of assigned for our fin pad that makes your life much easier. Okay. So anyway, now we can go to contact formation and doping. And how about contact? So here you can see some routines used to generate contact. For example, gate contact. This is a name used for our device simulation, but its region is currently given as gate. And now when you say this way, you can make the surface of this gate material, that part becomes the contact. So what does it mean? Here you have the surface of gate material, tungsten, that becomes gate contact. And interesting point is you can find also gate here and there. They are not separated. Although we have name gate contact, here we have the real gate and dummy gate, and they are all attached to this gate contact. So I think that it is better to eliminate this unwanted gate part for your efficient simulation. And another one is here we have a deep substrate, and here we have a different specification. Previously the type was this. This means that just the entire surface of that region is assigned as gate contact. But right now, when we say the side, then it just takes a certain side of given structure. So maybe you can feel that this is not that much general for general shape, so you have to apply it to box-like structure. And Z-min, so Z-min means that for example, if we have a box-like structure, then it can have 6 different faces, but this Z-min option that the surface underneath of this box, that part is taken as body contact. So you can see that this one is set as body contact. Although we have here deep substrate looks like this, only this bottom surface is taken as body contact. And here we have one interesting part, source drain contact. Source drain, if source and drain are connected to each other, then we cannot have the real current. When you just make the same potential for source and drain, then if they are equipotential, then we cannot have any kind of a drain current. So we must separate them. How can Mr. Zhang made it? Oh, I think that is quite clever. So here in this third line, we just make this using this type source drain contact. After that, we have source SD underscore contact. It contains both of this one and this one, just like a gate contact. But by select contact line shown here, it just separated into two parts, and one is assigned to source contact and one is assigned to drain contact. After that, the original one containing both of source and drain, that is just removed by this source drain contact. Okay, so just take them all and separate, and the original one is eliminated. That is the one we have. And how about the doping? I think that I made mistakes not attaching our input file, so I will also make the screenshot of my input file, but actually that is the same as our previous one. I just copy and paste it, and Gaussian profile was changed, or sigma value was changed to from 2 to 3. Why did I made that change? Well, number 2 nanometer or number 3 nanometer, that is not that off from the real world case. I think that is quite a reasonable value. I just made it as a simple exercise. Also, you can change that number. This is the final structure. Only silicon part. Here you have a diamond source and drain, Also here we have a fin. And when you just look at this fin part, except for source and drain, even in this case, you can find that here and there we have a certain doping. Initially, it was just a fin, so therefore it should be p-type lowly doped. However, by using the command shown in our example file, actually what he did is detect the interface and measure the distance from certain point and interface, and assign the Gaussian profile depending on the interface distance, the distance from interface. So that is the way we have this kind of a beautiful Gaussian profile. What is this? This one is the shape of our doping profile, n-type doping profile, seen from this direction. So now you can see that there is a certain dip in here. This is corresponding to 7 nanometer. Please note that initially fin was a p-type doped. After that, we introduce phosphorus containing silicon part to make this doping profile. So if everything is just as grown, then we will have just p-type fin, and here we have a highly n plus doping n plus diamond silicon epitaxial layer. However, of course, we anneal this one with quite a high temperature, although not that high, not that long time, quite a short time we apply heat. So during that one, we can expect a certain kind of dopant diffusion into the fin. So that's the reason why, although not as high as this original level we have assumed, but we can have a small amount, relatively lower amount of dopant in this one. So if you change sigma value here, then you can have even steeper dip, and if you increase this sigma value, then you can have a much smoother transition between. So please change it, play with these numbers to have this one, this shape. Thing is, if you change this number too high, sigma value, then of course the fin will become almost entirely n-type doped. That is good for source drain doping reduction. But what will happen? If you increase that number, then also it increased penetration of your n-type dopant into your source, your intrinsic channel region is enhanced. So simply speaking, although you have drawn 20 nanometer gate, but the effective thickness of or effective channel length of your transistor becomes shorter and shorter, and that will introduce the worsened short channel effect. So you want to reduce source drain resistance, but if the cost of that engineering is worsened short channel effect, then you cannot afford it. So short channel effect should be avoided at most, and so this is one of a typical example of a trade-off. You wanted to get some good property, but that is not independently controlled. You cannot make only fin penetration, not penetrating into a channel. That is not possible, because what we can do is just to increase heat or do some etching or deposition, this kind of basic skills. So therefore we need a lot of optimization for our structure. So now using this one, you can try to have an equilibrium solution, and please try your structure. This one is corresponding to, of course, source and drain, and this is our fin channel. And here we have a dummy gate and dummy gate, but it is just biased to 0. And after finishing this job, then I move to calculation of IV characteristics. But as I told you before, my workstation is fully occupied by my graduate students, so I was not able run my own simulation. So I stop here. So my recommendation is, today you don't have any official homework. Please just try to make your own FinTech file. But my suggestion is, later you must start simulating that FinTech structure. So that will be the basic starting point of your later exercise. So make it small as possible. So my suggestion is eliminate dummy gates and only have half of this active source and drain part. Then of course for that purpose, how can you do that? So please think about this one. Of course you can have different ideas. So well, so if you cannot make the exact reproduction of this shape, then I think that it is still okay. So it means that manage your structure in an acceptable level. Too large system will eventually demolish your term project. If you make a very beautiful structure and contains a lot of detail, but if that simulation cannot be done within given time framework, then that is a disaster for your final presentation. So please make a reasonable project for your score. Okay, so I think that's it. So today you have sufficient time to follow your previous film fact generation, and as I announced at the beginning of our today's lecture, we have no offline lecture on this Wednesday due to my business trip. So I will just upload YouTube lectures and just to watch it. The content will be just a continuation of this film flash simulation. So you also must follow that kind of device simulation. So please prepare your own structure, small structure, and be ready for our next lecture. Okay, do you have any question or any difficulty to do some exercise in our previous lecture? Okay, if not, so I want to wrap up today's lecture. Thank you.